Hi, welcome to my PowerPoint presentation on problem 1028 of Statics 15th edition. This is an extra credit opportunity as part of my Civil 2131-002 class at the University of Memphis. My name is Wyatt Wallerenta, and I'm a mechanical engineering major. This is part of fall 2023, and the date today is December 2nd, 2023. Right, so getting on to problem 1028. Determine the moment of inertia of a beam's cross-sectional area with respect to the x and y centroidal axes. The first thing we should know is, what is moment of inertia? In my words, the moment of inertia is a value used to determine the likeliness of an object to deform. Our object here is an I-beam, which is a very stable structure, but we don't know why it is. Using moment of inertia and finding the centroid of it, we can calculate a value that will tell us if something is more likely to bend or not. A perfect example of this would be if we had two identical beams. For this example, let's say it is a 4-inch by 2-inch beam. And we applied a 10-pound load to the center of mass of each, one on its 4 side and one on its 2 side. Most people would say that on object 2 right here, we're going to make this one 2 and this one 1, that object 2 is going to be more stable than object 1 and would be better for holding it, wouldn't deform as much. But why is that? Well, using moment of inertia and drawing a centroidal axis, and a centroidal axis is an axis that the centroid sits on. For our example, an I-beam centroid is directly in the center due to its shapes. So the axes will be along the centroid's axis, which here we'd have X and here we'd have Y. The same thing for the rectangles. I'm just going to draw the X for here. It would split the middle of this X. Okay. Now, as you see in number 2, they're going to have the same area. You can calculate it, and we can go 1 by 4 and 2 by 2. We're still going to get 4. But object 2's material is further away from the centroidal axis on a distance, which is going to give it a higher resistance to deform compared to object 1. Now, with that information, we can move on to the problem. All right, breaking down the problem. Starting right to left, we're going to take a look at the I-beam separated into 3 different shapes. The 3 different shapes we're going to split it into is 3 rectangles. Now, we can do it in a different way. I'm just going to be explaining it using this method right here. But I will touch on the other method at the end of this slide. So, of the centroidal axes, with our middle picture right here, a rectangle is going to have a centroid directly in the middle, which its axes would be right along the middle as well, given the half value between the X and the Y. It's going to be, the centroid is going to be the half point of each. So that's why we have 3 different centroidal axes here. Okay, and what we'll do is we'll find the moment of inertia of each of our shapes, add them together, and that's going to give us the total moment of inertia of the shape. And I want to just show you the parallel axis theorem, okay? And why we have an area times a distance squared, whereas we don't have an area times distance squared here. And this is going to be a very important part of this problem in particular. Now, when we are given the shape itself as from the book reference, the middle picture, so centroidal axis is going to be directly in the middle. Now, we measure this distance, the area times the distance, from a centroid, from the middle centroidal axis of a shape. So for our I-beam, for example, it's going to be directly in the middle, right along this X. But when we take another centroid of another shape, for example, this top rectangle, there's a distance now associated with the centroid from its centroidal axis for the X, but there isn't for the Y, because we can see that the y goes right in the middle, and it'll just run right up. So in this case, if we didn't use our area times distance squared, we're not going to get the correct value. The book doesn't give us this example because the centroid is directly in the middle, which makes it negligible, right? If this distance is equal to 0, so if I took the area times a distance 0, it would give me 0, making this 0. Okay, I just wanted to make sure we're doing that. And also, this is for an x value, base times height cubed. There is a small difference between them, and just take note of that. Now, the other way we could do it is thinking of it as another shape. We can say, you know, well, maybe it's a big rectangle. We could see here that we have 1, 1, and a 6, making this 8 total. And we could have 2.5 and 2.5, which is 2, okay? Or 5, sorry. Then we can say, well, if we have a huge rectangle, right, we can draw centroidal axes right in the rectangle. We could say, well, maybe we have a big rectangle and we cut out 2 other rectangles, which would be sort of like this, but we can see it depicted here. And we could do it this way. This way does have its benefit due to we are always going to be in a centroid, so we wouldn't have to take this distance, which would make it negligible for this. But this isn't the way I'm going to be showing it. This is just the way I wanted to explain in case you see it anywhere else, or you see something and you're trying to, you're kind of confused about it, why and why not. This is why, because the distance is 0 from the centroidal axis when we take it directly in the middle, when we do it this way. And we can give these shapes. We can say this total, we could just make this 3. We can make this shape 1 and the shape 2, even though they would be the same. Okay, and we could say 3 for both is equal to -1 and -2, which would give us our total. Okay, and when we do this, we would still have to plug in our x and our y for each of these values here. Okay, just wanted to show that there's different ways we can do the problem. I'm going to be showing the axis theorem through this problem. Perfect. So compared to the last slide, I imported everything about the same and tried to do my best to keep the colors the same. I didn't happen to have the same pink as my drawing program, but we'll make do with that. So given the shape here, we have the centroidal axes, and we know that the centroid of the main object is going to be right in the middle, okay? And when we're going to break this down, we're going to put 2 more centroids, okay? And these are going to give us our 3 shapes that we're going to use, okay? So now let's take a look at shape 1, okay? So shape 1 here, using our formulas at the bottom as provided, it's going to be the base times the height cubed plus the area times the distance squared. Now, I'll write it right here. So we have that 1/12 base times height cubed, area times distance squared. So let's break down how we got these values from these shapes. We'll use purple here. So this is going to be our base, and this is going to be our height, okay? Now, how we see this is we say 2.5 plus 2.5 is equal to 5. So we know this value right here is 5 inches. And that's how we're going to get 5 inches. We know the height right here is 1. So we get 1 inch. And the area, I'm going to write it right at the top because it's going to be a very common thing we're going to use. An area for a rectangle now, it's going to be different for other shapes. It's going to be, it could be the height times the base, but that just doesn't sound right. It's going to be the base times the height. Now in this case, remember, we have a base of 5, and we have a height of 1. making it inches squared. And the way that is because it's 5 inch times 1 inch. And when we multiply inches times inches, it's going to give us inches squared, which units are important in engineering problems. So always pay attention to that. Now, the area we got right here. Now, how did we get a distance of 3.5? Well, for each of the shapes, they're going to have their own centroidal axes because they have their own centroids. It just so happens that the y doesn't move because it's along the main centroidal axis, giving it the 0 value we have right here, okay? With respect to the y centroid, it's going to be that the x will be the 0 right there. So besides the point, we have the x axis. Now, how far is this from our main centroid for our object, which was directly right here, okay? Well, we see that this total value is 6. So half of it is going to be 3 inches. And we see the total height is 1. And we know a rectangle's centroid is half of the total distance, making it 0.5. Giving us this distance is equal to 3 plus 0.5, which gives us 3.5 inches. Now, checking our units. Always check the units. It's super important. So we have base times height cubed, which is inches times inches cubed, plus area. Remember, area is in inches squared, so we have inches squared. And distance squared, which is in inches squared, giving us inches to the 4th plus inches to the 4th. And that's how we get inches to the 4th. So very important that we keep those. All right, so now looking at shape 2. Shape 2 is going to be our green shape. And we're going to have the same thing going on here. We're going to have the base times the height times the base cubed. We're going to have the area, the distance, and the distance. Okay? Now we see that our shape is directly in the middle, which is why these are going to be negligible, because when we multiply it by 0. And our shape right here is going to have a base of 1. And is going to have a height of 6. Okay, and that's how we get the 6, the 1 for the base. And there, and same thing back here. We can also make sure we're just checking our work really quick. We have the height and the base cubed, right? The 5, perfect. Height, 1, perfect. Okay. Which is going to give us 18 inches to the 4th for this shape 2 and 0.5 for the inches to the 4th for our y. Okay, now moving on to shape 3. Shape 3, if we're using intuition a little bit, we could see that shape 1 and 2 would be identical to each other, which is going to give us a replicated value or a repeated value, in a better words to say. So we can almost double check our answer by doing that. If we didn't want to do this, we could just multiply our shape 1 by 2 to give us the value. Because in the end, how we're going to do it is we're going to add all these values together, and this is going to be our final answer. So we're going to take the 61 plus 61 plus 18. Remember, these are all in inches cubed, or inches to the 4th. My apologies. So we have the 61 to 18, perfect. And that's going to give us 141 inches to the 4th for our x, moment of inertia. And for our y, we're going to have 10.41 plus 10.41 plus 0.5 inches to